started at 10 after the hour, roughly 5 or 10 after the hour. You have 40 minutes to take a 25 multiple choice question assessment. I would say there's, and this is not in exacts, there are ranges, but there's about 4 or 5 questions on spectroscopy, probably about 8 or 9 on reaction chemistry. There's a few on stereochemistry, and then there's some on, will be the acid-base chemistry, will be the last one, okay? There might be a random question or two on stability of molecules and those sorts of things, but that should all be okay. We've pretty much reviewed for the assessment, especially today we'll be here talking about the last of it, right, to remind you of the few last things. And maybe you forgot about reaction chemistry from last term, but that's about the framework for the assessment on Wednesday. So it's heavy on reactivity, it has some acid-base chemistry, it has some spectroscopy, and it has some other categories, okay? So you should, if you've been doing everything all along and been following along with the class, we really have reviewed the skills for the test. Okay? Are there any questions before we get going today? Mm-hmm.
So when you say reaction chemistry, do you mean we should know mechanisms?
No, so there's nowhere, I mean, it's very hard that, you know, you're never going to be asked to reproduce a full mechanism on a pre-assessment, right? Because A, that takes up a lot of paper in an A, B, C, D category, right? But when I say reaction chemistry, I'm really talking about outcomes in terms of 1 or 2 steps. You know what the product outcomes are going to be, remembering about regiochemistry and stereochemistry. So I'm going to try and throw that all in today to try and see how many times I can trick you, so I can trick you today and not on Wednesday. Yeah? No, terpenes are very interesting though, right? That unit is a very interesting unit. It's found a lot in food and flavor chemistries. It's a pretty amazing little section, but no, you're not going to be questioned on that. The main framework from chapter 17 is to understand the difference between benzylic and allylic, or to understand the importance of benzylic and allylic sites in terms of SN1, SN2, E1, and E2. Okay, so that's the important part. Okay, yes. So when you say reaction chemistry, right, like I said, you know, in class, you take a reaction, I mean, this is very simplistic, but, you know, you could do something like this and get something like this. So you could be given these two and asked for the product, right? You can be given these two and asked for the reactant, or you can be given these two and asked for the conditions. All of that's reaction chemistry. I'm not suggesting in any way that all the questions are, I give you the reactant and the conditions and you just give the product, right? They actually go all sorts of different ways. Can you know the reagents? Can you give the reactant if this is what you reacted it with to give products? So they are asked in all variety of ways. Yeah?
So looking over the door prize that you gave us was
Yes.
pretty helpful, right?
Looking over the door prize is helpful. Now, the one thing the door prize doesn't do, which I'm going to try and add today, right, is that embedded stereochemistry of all these things. Now, I've been talking about it all along, and I've been categorizing, and I've been using that language, but I haven't necessarily been doing examples like that. I've been trying to get you back to the regiochemistry, right, which is where things go. Where does the nucleophile add? Where does the electrophile add in an EAR reaction? Or what type of mechanism is this going to do? SN2, SN1, E1, E2. I've been trying to review those sorts of things, right? But now I'm going to today come in with not only those types of questions, but stereochemistry as well. Because there are some straight regiochemistry questions, and there are definitely questions that embed the stereochemistry as well, which we do need to know. Okay? All right, great. So let's start with some alcohol review reactions, or alcohols, ethers, and epoxides, I guess, would be really what to say. So here's one type of question, which is a classic question in terms of understanding stereochemistry. So if you started with this alcohol, the question is, what 2 paths, because you have to take 2 separate paths to get to now these 2 product outcomes, which are different. And how are they different from one another? Stereochemistry is different, right? So one, we would say, retains the configuration at the center. Okay, so the top path is what we would call a retention of stereochemistry. Okay, the wedge is where the OH is found, and the wedge is where this cyano group is found in the end. And the bottom one is what we would say is inversion of stereochemistry, right? Because we have a wedged OH to begin with, and we have a dashed CN to end with. So the question is, by what 2 paths do we get to each of these molecules? So in order to do that, you can either work forward or work backwards, right? The idea is that you're replacing a CN for an OH. Now, hopefully none of you are thinking that HCN is going to do that, okay? Because HCN won't do that. You can analyze the acid-base chemistry because that's a classic answer on a Chem 1 final, Chem 231 final. If you analyze this acid-base chemistry between an alcohol and HCN, right? And you say, okay, I'm going to get ROH2+, which is what would be necessary, right? Because you need a good leaving group. Alcohols themselves are not good leaving groups. So we usually use acidic conditions to make H2O, right? Still attached and hope to get some displacement. So the question is, which direction does this acid-base chemistry sit? And this acid-base chemistry sits to the left and not to the right. So you cannot use HCN to do that, okay? So that's out. So that was one trick we could use to make a better leaving group for the alcohol, right? Was to run reactions in acidic conditions. You saw that with alcohols and hydrogen halides, right? Or alcohols and H2SO4 and heat. Those ran SN1 or E1 reactions respectively. But what are the other two ways that you know you can make a better leaving group? Tosylation is one possibility. Okay, so tosylation, when you take something that's a tosylate, and I'm just going to simplify this example as we move forward. If I take PTOS chloride, right, which would have to be run in pyridine, if I do this, you do get a better leaving group, which we call a tosylate, okay? So that's OTS, if you remember tosylation, p-toluene sulfonic acid, right? It's this large, we always TS'd it, we always call it TS. But remember that this first step comes with maintenance of stereochemistry, meaning no inversion. To tosylate means just exchange out an H for a tosylate. There's no change to the stereochemistry at the carbon center. So that is absolutely a possibility. And now I have a good leaving group, right? Tosylate is a good leaving group. What do I want to replace my leaving group with? CN. So I would want to run this reaction with something like NaCN, because NaCN is just a cyanonucleophile. And the cyanonucleophile at a secondary site is indeed going to run SN2 chemistry, right? I have a secondary alpha site with a nucleophile that I would consider moderate. A moderate nucleophile is going to run SN2 stereochemistry, and I'm going to get inversion in my example here on the middle board. So I can see that these two steps can be applied to get which product here? The top product or the bottom product? Bottom. Okay, so here this is to tosylate in the presence of pyridine, and then to run NaCN in some sort of aprotic solvent. You're not getting dinged on the solvent at any point in time. You weren't dinged on the homework. You're not going to get dinged during an exam, but I'm just telling you, you need an aprotic solvent, just so we're absolutely 100% clear. The top path then isn't going to go by tosylation. What is another option to create a better nucleophile? I mean, a better leaving group, better leaving group from the alcohol. PBr3, or thionyl chloride. That's exactly right. So you had two potential paths, right? One was to use PBr3, right, also with pyridine, or you could run thionyl chloride, SOCl2, with pyridine. One replaced, right, the OH with a Br, that's what PBr3 would do, and one would replace the OH with a Cl, that's what SOCl2 would do. Those both came with inversion of stereochemistry in this very first step, right? They both came with inversion of stereochemistry in this very first step. So let's say we follow through with PBr3 here. So that's going to give me a Br in a dashed configuration, right? Because you're going to see an SN2 inversion when you use thionyl chloride or PBr3. So when I run my second step, which is also simply NaCN minus, right? So salt, it's going to do SN2 again, which is going to lead to what we would say is an overall retention in the stereochemistry, right? An overall retention of the stereochemistry. Does everyone see what I mean here? So this here is going to be something like PBr3 in pyridine, followed by NaCN and some sort of aprotic solvent. Okay? Everyone remember this? Are there questions about this example? Okay. All right. Next up on the block is this guy here. Shut up for a minute. Just a minute. Okay. So the minute I just see halogenated compounds, I know I'm in my SN2, SN1, E1, E2 pool, right? So I've got to, once I start to see that starting material, that's what I'm going to begin to think, right? No double bonds, so I got to be SN1, SN2, E1, E2. I also knew this was similar, just to go back here for a minute, because the double bond never changed, right? I never did anything to the double bond. It was still in my products, right? So I knew I wasn't doing EAR there as well. So, question is H2O heat. What type of mechanism is that? E1, right? An E1 type mechanism. Here again, the updated flowchart is online, so if you want to go get it, it is there, okay? But this is a secondary site to do SN1, SN2, E1, E2. So now I classify my nucleophile. My nucleophile will be classified as weak because I make the conjugate acid of H2O. And the conjugate acid of H2O is H3O+. Its pKa is -2, roughly. So it's what we consider a weak nucleophile. Weak nucleophile is going to do SN1, E1, but when heat is present, it's going to do E1. Okay? Please don't forget about rearrangements of the backbone with SN1 and E1 type mechanisms. Okay? This actually is going to do loss of the leaving group to create now this carbocation. This carbocation is going to rearrange, right? It's going to do a hydride shift to give me now this carbocation. And this is the carbocation from which my reaction E1 specifically is going to occur, right? Because E1 is first generate the carbocation intermediate, work toward the most stable carbocation intermediate, and then work toward the second part of the mechanism, which is beta elimination, right? To use H2O to pull a beta proton in order to give the final product, which in this case is the more substituted alkene. So E1, no matter what, is always going to give you the more substituted alkene. It will also give you an E alkene over a Z alkene every single time, because E1 is only getting down to that most stable product. Okay? Does everyone see what I mean about the rearrangements? Okay. All right. Second one, NaOH and H2O. What type of mechanism is that? E2. Because I skip over my solvent, I make my OH minus, and I say, what's the conjugate acid of OH minus? It's H2O. What's its pKa? 16. That makes it a strong nucleophile, and strong nucleophiles are going to run E2 reactions. They're concerted, they're one step, and they're looking for the anti, right, hydrogen. At the beta site, the hydrogen has to be anti. So the question is, which of these sites has a beta site, right? Beta site 1, beta site 2, I'll label them beta site 1, beta site 2. Which one of them has an anti-hydrogen? 1, right? This site here does not have an anti-hydrogen, correct? Because an anti would mean that it's in a dash, right? If this Br is in a wedge, the hydrogen here has to be in a dash. But what's in a dash at this site is the methyl. The only hydrogen at this site happens to be in a wedge, and that's not anti. So I have to pull from over here, because it's the only site that has a wedged, right, dashed, you can see I'm a little bit out of sorts, a dashed hydrogen, okay? So in this case, I'm going to get an alkene that looks like this, where the stereochemistry is maintained down here at the methyl. Nothing happened down there. So there's going to be no change in its stereochemistry, right? So this is what I get out of that. How are we doing? Yes? So I know it's not SN2 because this nucleophile's conjugate acid is H2O. And H2O's pKa is 16. Anything that has a pKa over 11 is going to do E2 at a secondary site. Remember, we have that way to break down SN2, E2, SN1, E1 by using the pKa's of our conjugate acids. Okay? Okay, and this last guy is going to run by SN2 because it's a charged nucleophile of a moderate, in a moderate category, right? It's acetate, its conjugate acid is acetic acid, whose pKa is 5, therefore it's moderate. Okay? Conjugate acid of this nucleophile is moderate, hence it's going to run an SN2 reaction. And an SN2 reaction is going to run then for the inversion at that brominated site. Okay? Yes? Are there questions about any one of these? Yeah. I know that because I'm reminding you of what the stereochemistry is of that reaction, right? So E2s require a beta hydrogen that's anti. That is the requirement. Okay? Other questions? Okay. Go back to a couple simpler ones just to see if we can't trick you on the stereochemistry a little bit. So, I'm going to write up a reaction. You're going to tell me what the product. I'm going to give you a multiple. It's like a multiple choice. Multiple choice. Here we go. It's what we call a twofer, right? Because it's not apparent right away. So you have to do a little bit more soul searching to get to this answer. So we have to start with, there's obviously an E2 product here, or E1 if you wish to think that's E1, but it wouldn't be. E2 or SN2, it's really your only choices. And I know that because my nucleophile is charged, right? Charged nucleophiles generally run E2 or SN2. You've seen that again and again and again. So the question is this E2 or SN2? Okay, we're going to do the same thing. Conjugate acid is H2S. H2S is a pKa of 7. Moderate nucleophile. Tell me, E2 or SN2? SN2. Okay, you got to get those pKa's down. It's really going to hurt you. So the E2 products are out. Okay, E2 products are out. So now I'm at an SN2 product. So now, which one is it? The one on the left. Okay, it's actually this one. So how would you go about solving that? How'd you solve it?
The one on the right, the same stereochemistry as the one there.
Okay, great. This product has the same stereochemistry as the starting material. So I need to go back and assign the configurations to the starting material. The starting material's configuration, putting in the priority assignments here, is R, because my fourth priority group is back, right? My fourth priority group is a hydrogen. It's in a dash position because that's the one missing here, right? So it's back. So that's R. So when I come down here, I need to assign the configurations to my products. So this guy is 1, 2, 3, and this is S. This has an S configuration. Hence I know, right, that this is the product. If you check this one, you need to remember that one little trick, right? That this is 1, 2, 3. It appears S, but the hydrogen is coming forward here. And when your fourth priority group is on a wedge, you have to flip the configuration. So this configuration at this center is actually R. Everyone remember that? R. Okay? What if I showed you these as Fisher projections? Could you do it as Fisher projections? Okay. Make sure you remember that a Fisher projection has the central horizontal axis here on the wedge. And the vertical axis here is actually dashes, right? You got to remember that about your Fisher projection in order to be able to assign configurations. So you would do the same thing. You would make the priorities at your groups. You would assign a configuration first. See if your fourth priority group is on the horizontal line, and if it was, you would flip its configuration. Yeah. So like one example would be something like this. And one would be, it wouldn't even matter, let's say, we just do it to Nancy, it would be fine. And one, say, could be like this. I mean, you can see they're enantiomeric here, right? You would know if you assign configurations. But this guy is 1, 2, 3. This is R. Okay? So that's not the right one, correct? Because that's the same configuration as my starting material. And this guy is 1, 2, 3, hydrogen vertical, so this guy is S. I keep the configuration. So that is the right answer in terms of the Fisher diagrams, as opposed to the dash wedge diagrams. Yeah? Okay, that's good. You guys are looking really angry, and it's so hard to be up here when you look so angry. Okay, so yeah, go ahead.
Shouldn't the H be on that dash line there?
I am not drawing Fisher projections that exactly match those dash wedges in any way. I just drew two different Fisher projections. They're not a match to those. Yeah.
If you have a strong nucleophile, but the leading group's on a primary site, should it go to SN2 or U2?
SN2. The question on the floor is, if I have an alpha site that's primary and I have a strong nucleophile, what's it going to do? SN2 is the answer. The only time it's going to do E2 is if you had a bulky strong nucleophile, right? That's when E2 will be the dominant product, okay? So that flow chart that's online is really helpful. You can kind of memorize the flow chart and utilize it for some of your assignments. You honestly will find it abundantly helpful. It does require that you know the pKa's of acids, of your conjugate acids, but that also is very helpful, okay? All right, trick number 3 from starting way back is something like this. These are to get diol products, right? Diols. There's 2 ways that you learned in OChem 1 to get diols. What do I have? Yeah. Yep. Epoxide ring opening is one of them. Okay, so we're going to try and just put together what we know to be the ways to get diols. So one way would be to get an epoxide. So following through from that starting material, I would say, okay, I'm going to generate an epoxide. So we'll use your famous MCPBA here. And I would get then something like this. They always look so weird, but this would be actually what you get from that. Okay? And then you would do a ring opening. And in this case, it wouldn't matter if I did an acid-catalyzed ring opening or a base-promoted ring opening, right? Because each of the sites are equally substituted. You remember that acid-catalyzed ring opening happens on the more substituted center, and base-promoted ring opening happens on the less substituted center. Again, it doesn't matter here, so we'll just do H2OH+, since we haven't done much acid-catalyzed stuff. We'll stick to that for right now. And so the bottom line is I would get to this product here, okay, as my final product, okay? So the intermediate epoxide I got, right, because I know that the relationship of the two methyl groups in the original alkene were trans, and I need to maintain that. And I know my epoxide is a syn addition, right? So that makes sense, right? Because the two bonds, that same oxygen, have to be on the same side. They can't be on opposite sides. So I maintained, right, what I know to be the relationship of the two groups in my original alkene, and I've done the syn addition, right, meaning those two bonds that have added have to add to the same side. So this is one potential way to draw the intermediate. And then I know when I do my ring opening that my two groups, my two OH groups, have to be trans to one another, or anti, because the nucleophile always has to do backside attack when we're talking about epoxide ring opening. So the epoxide ring opening leads me to this. What's the other way I know I can get to a diol?
Osmium
Osmium tetraoxide, that's right. So osmium tetraoxide. You guys are really bad with your numbers, and this is where people lost a lot of points on your stuff. This has to be 1 osmium tetraoxide, 2 NaHSO3, not like osmium tetraoxide, NaHSO3 at the same time. That's not going to do it. It has to be step 1, step 2. You do that with hydroboration too. You add BH3 and then everything together. That's not it. You have to have 1 BH3, 2 H2O2, and so we're going to try and train you that way as the semester goes on. But this will absolutely give me what I know to be a syn addition here. So this is one potential stereochemistry of products that I can get. Okay? So how am I going to be able to match those? What do I do? In a multiple choice setting, right, I have to be able to match it to the products. And those are the products there on the left board. I would use configuration, right? That's exactly how I would match it, okay? Because one of them led to eventually a trans relationship between the two OHs, and one led to a cis relationship between the two OHs. Now, you guys get very caught up in how these things look, right? How the products look over here on the left side, because you don't see that cis or anti-relationship, right, between the two OHs. So you're like, well, I don't know. I don't see the cis or anti-relationship, right? So what you have to do is you have to rely on configuration. Come back to your starting material and do what we did, right? Make an anti-one or a syn one, assign the configurations, and find it based on those configurations, right? Because every straight chain sigma bond has 6 diagrams that I can draw, 6 dash wedge diagrams that I can draw, right? All still representing the same molecule. So if we start matching, this guy's going to be 1, 2, 3, R, and this guy's going to be 1, 2, 3, R, but S, right? So this is my meso compound, RS. So I'm going to look for that over here. This guy's going to be 1, 2, 3, S, but it's R, and this guy's 1, 2, 3, 1, 2, 3, R. So this isn't it, so this has got to be it, okay? So this is my meso. That's going to be RS. This is 1, 2, 3, S, and this is 1, 2, 3, R. Here it is. That's my meso compound, right? You don't see it as meso right now, I totally bet, right? Because you see a diagram and you think of it as static, but it's not static, right? It has free rotation, and one of its conformers will actually have a plane of symmetry that will identify its meso status. But I can tell you that if you have 2 configurations in the same molecule, one with R and one with S stereochemistry, it is indeed a meso compound. The plane of symmetry is there, you just don't see it at current, okay? So we're going to see how I did this. This is embedding that stereochemistry into the reaction stuff. Yeah?
So could you just repeat the last part? If it's S and R, it's probably meso.
Yep. So if you have 2 configuration, if you have 2 stereocenters, 2 asymmetric carbons, same substitutions. So in this case, they each have an OH, a CH3, and H, and then the other side, right? One is a configuration of R, and one is a configuration of S. That is a meso compound. There is a conformer where you'll see a plane of symmetry. Okay? All right. All right, so how about some synthesis stuff, like reagent stuff? Here we go. posit the answers later today. We're only going to do a few of these, but this should be some synthesis practice for you. So we're going to start each case with this guy here. You're going to tell me how to get to all of these things. You write that down. Alright. I think I want to start with this one. Talk about how we're going to get there. We're going to take out that one line there and see if we can't figure out how to get from one to the other. So the one thing I note is that I have added carbons, right? We pretty much see that, right? Now, adding carbons at the terminal ends, termini, can happen through an alkyne or an epoxide. Hopefully that's logic to you. It can happen through an alkyne or an epoxide. But adding carbons internally has to come from an epoxide. There's no way you're going to get internally to add carbons using an alkyne, because internal alkynes cannot do that, right? It's only terminal alkynes that have a proton that you can pull to extend the chain, right? So internal alkynes are never going to do that. So if you add any carbons to your chain internally, then it has to be through an epoxide, of which this is an example. Okay? This is a prime example. I didn't add two methyl groups like out here, right? Or two carbons out here. I added them internally. So this had to have been from an epoxide. Now, to do an epoxide, to the best of my ability, I want to have a less substituted side, right? I don't want to have equal substitution on my sides, right? So if I think back, right, one step, I would have come back to this guy here, where I had now an epoxide here, right? Or did I have an epoxide here? I guess I should have formed that more as a question. Did I have an epoxide here, or did I have an epoxide here? Which is it? Because I'm using this carbon, right? This is one of the carbons that I'm using in my epoxide. That's where my addition went, right? So I know that is a carbon of the epoxide. I know that. So the question is, which one am I going to use? The one on the left, right? So this is out. because this allows me for a less substituted side and a more substituted side, right? The less substituted side where my ring opening can happen, right? And then my more substituted side where it will not happen at, okay? So I know I came from this, all right? So the question is, if I come back one more, so we're going to come back even one more, I know then that my alkene had to have been this guy, right? Because it's only this alkene that allows me to get to the epoxide shown, right? So I know I can get from here to here, and I know I can get from this alkene to this epoxide. So how do I get from that starting material to that alkene? I can do elimination, but elimination is only going to make it on one side. It's only make the double bond on one side. It's actually a trick. The trick is to just bring it down to the alkane and then add Br2 in light. It'll always get you to the more substituted center in a molecule. So if you took this here, so we'll work on this board maybe over here, you took that starting material and you made an alkene first and then used H2 platinum. Yeah, I guess you can move the double bond a couple times over too, but that seems to be a pain, right? So if I took this guy and I ran, say, NaOH and H2O, I'm going to get this alkene. If I do H2 platinum now, I'm going to get just the alkane. And now if I do Br2 in light, which we said we're always going to use NBS now, right? If I use NBS, I'm going to get this molecule right here. Okay? So this is always going to get me to the more substituted side. And you can see that I want to be moving over to that more substituted side. So one trick to do that, right, is just to get rid of anything you have in there and use NBS, right, to brominate at that more substituted carbon center, which will absolutely get you into where you want to be. Okay? Yes?
Could you say that again?
So one trick is if you have a functional group way away from the most substituted center, but you can see all of your new functionalities, right, are toward that more substituted center, what you want to do is just get rid of that functionality and use NBS to make this alkyl bromide. Now you're working over in the area of the more substituted center, right? So that is one trick that we use, right, is we add some things out in one area and then we want to just stop working over there, right? So we have to have some way to get back to another area in the molecule. And this is one way we can do that.
So it's like MBS, you could just add a BR wherever you want to go, right?
Okay, NBS will add a BR to the most substituted, most stable center. So in this case, I have secondary, tertiary, and primary. So this is going tertiary. If I had benzylic and allylics, they would be going to those sites preferentially, right? But I don't have that here. Okay. Yeah?
Why would you use one of those?
It doesn't matter. You can use an aprotic solvent. Just generally OH minus comes. It's easiest to buy it. Cheapest to buy it. H2O and NaOH. It's very odd but true. It's all just a cost-effective thing. Okay. So now I have a bunch of things that I'm stringing together. We see the first three steps. I've written them out over here. Okay. You know how to get from how do I get from that brominated molecule to my alkene? Just elimination, right? So NaOH, H2O, totally fine. Okay, great. How do I get from there to the epoxide?
MCPBA.
MCPBA, great. Now I'm at the fact that I want to add my alkene, or my alkyl group here, okay? So we're here. We're going to pick up our synthesis here, okay? I want to add my alkyl group. I'm, in essence, going to do now nucleophilic ring opening. When I do nucleophilic ring opening, so we're going to come forward a couple steps here. Now I'm at that molecule over there, which is this one. So now if I add ETMGBR followed by H2O or H plus or something, I'm in essence going to get, I'm working there. Now I'm here. Okay? So I'm almost there. This is what I get as a direct result, right? Yeah? Because this epoxide here on the left is going to ring open exclusively here, which is what I want, right? This epoxide over here can ring open here or here. It's not going to give me the backbone I want necessarily, okay? You always got to find the best reaction. Okay, so we're here. Now what am I going to do? What do you think? What am I, again, I'm getting so close, right? I'm getting close.
PCC.
Well, PCC isn't going to work here. Good idea, though, to make that carbonyl, but it's not going to work quite yet. Why won't PCC work on this? Actually, another good trick question. Yeah?
It's a tertiary.
It's a tertiary site. That's exactly right. You can never oxidize at a tertiary site. Good trick question, even on an Orgo 2 exam, because people forget that. So a tertiary alcohol will not oxidize. It has to be secondary or primary. So good? So what do I need to do? I need to kind of move over, right? I need to get back over here, really. You guys can work from here. See if you can't get it back over to here. Okay? You got to move your functionality, your OH, back to that site over there, right? So you can get it. Now, some of these reactions that I'm about to review for you are going to be things that you want to utilize. Okay? Just want to get you thinking synthetically here. All right? I've already given you one. Number one on my list in synthesis is make sure you create an epoxide that has a less substituted side and a more substituted side, right? Such that you can always open at the less substituted side with a Grignard. We've already talked about how to carbon add, whether it be at a terminus or to carbon add internally, right? The use of an alkyne versus the use of an epoxide. But then there's some differences in regiochemistry that really are going to sell you, and those are the latter things that I want to be able to review, and you are going to utilize some of these as you work through these synthesis, okay? Number one is the difference between brominating, right? This is on your sheet, this is on your door prize or whatever, but you need to know these for synthesis, right? So I'm trying to make sure to review the things you need to know. One is the difference between HBr and HBr and peroxide. Because HBr is always going to leave the Br on the more substituted site, and HBr and peroxide is always going to leave you on the less substituted site, right? Very useful to you. Very useful to you. Matter of fact, you'll be utilizing that, okay? Another is the difference between H2O, H+, and the hydroboration reactions, which you've already utilized and you've seen in hopefully that homework, right? Sold the necessity to sort of remember these things in a review capacity, okay? What's the difference though, because this is one last one that's really quite useful to you. What is the difference between H2OH+ and mercuric catalyzed hydration? If I say had this molecule here, and I did one with H2OH+ and one with HgOAC2 in water, followed by sodium borohydride. What's the difference between them? Yeah.
It reassures that your chemistry, but like the same way. HgO and like mercury catalyzed HG. That one would ensure that it stays in alcohol. Or the other one might be using a little bit of another.
Okay, you're so close. You're so close. Yeah.
One's more prone to rearrangement.
One is going to rearrange and one isn't. Big deal. That's a huge deal to us. Okay? So in this case, your major product is going to be some achiral alcohol, right? Because it's going to rearrange to the most stable carbocation. It always does. Whereas down here, your major product could either be RS here with a methyl group here, or RS here with a methyl group still on there. That's indicating no true stereochemistry at that methylated site. But you're never going to rearrangement because there is no carbocation intermediate, right? There's no true carbocation intermediate, okay? They do have a difference in stereochemistry, I totally agree. We wouldn't have necessarily seen that here, right? BH3 is syn, mercuric catalyzed hydration is anti, right? And H2OH plus gives us both stereochemistry. So there's definitely a difference in stereochemistry. But the fact that one won't rearrange and one will is actually quite a big deal, okay? So these tricks here will help you in here. And these are the types of functionalities we're going to be dealing with this term. So I'm trying to be very decided, right, with the way I'm reviewing to make sure that we're going to be good and set up to go when we get into synthetic schemes here in Orgo 2. Okay? Are there any questions left on the floor? Okay, I will be in my office tomorrow. I will see you on Wednesday.
You said you're going to post that
I will
training.
post the answers to these tonight. Yeah, I'll go home and do it right away.
You're up.